Now that we've gotten a look at how a hypothesis test for one proportion can work, we're going to do a few more examples. This next example is going to look at a right tail one proportion test. Let's say that we have a dog, Shampoo, that claims it kills more than 25% of fleas. And a dog with 42 fleas is shampooed and 18 fleas are killed. We want to know, what can we conclude if alpha equals 0.01. So again, we're going to go through the same 6 steps that we went through with all of our hypothesis tests. The first thing we need to do is identify the hypothesis. So our null hypothesis, we're talking about a proportion or percentage of fleas that are killed, is equal to the claim of 25%, which is 0.25. As an alternate hypothesis, what we're trying to prove is that it actually kills more than 25%. So that p, what we're trying to prove, is greater than 0.25. And so as our next step, as we try and draw a picture of what is going on, we'll have our normal distribution with the mean of 0.25 that was claimed in the middle. But this time, we want a right tail test because we're going to try and prove that it's greater. We have a right tail test. And if we want to know exactly what that proportion is at the edge, we can find p hat from our sample. Let's go ahead and find it now. 18 out of 42 fleas were killed. That comes out to be about 0.4286. So that's the edge of this shaded region, 4286. After drawing a picture, we're ready to find the test statistic. For the test statistic, the first thing we need to find is the standard error. The standard error, you remember the formula from a prior video, is the square root of pq over n, where p and q come from that null hypothesis. So p is 0.25. Q is 1 minus 0.25, which is 0.75. And then we divide by our sample size. There were 42 fleas. And when we do that on our calculator, we'll end up with 0.0668. Once we know our standard error, then we can calculate the actual test statistic z. Z is found by taking our sample proportion p hat, subtracting the claimed proportion, and dividing by the standard error. So in our case, 0.4286, the sample proportion minus the claimed proportion of 0.25 divided by the standard error that we just found, which is 0.0668. And that's going to give us 2.67 for our test statistic. Now that we know our test statistic, we're ready to calculate the p-value. The p-value we find using Excel, and we do it with the norm.s.dist command. But if I look at the picture, norm.dist will give me the area to the left. We want the area to the right. So we need to make sure we account for that in Excel and do 1 minus norm.s.dist. And then we do the 2.67, and we do the true. When I do that on Excel, we should get 0.0038. A good check to do with your p-value is if you're only shading one side of the distribution, the p-value should be less than 1/2. If it's more than 1/2, you probably have the wrong tail and you didn't do the 1 minus. Now that we've got our p-value, though, we're ready to make a decision. Since we said our alpha was going to be 0.01 and our p-value we just found is 0.0038, the p-value here is smaller than the alpha. So when we have a small p-value, we have passed the threshold for believing the null hypothesis. We've gone beyond a reasonable doubt. And so with the p-value being smaller, we get to reject the null hypothesis. If we have rejected the null hypothesis, then we can interpret this result in context for what we're actually looking at. So looking at the alternate hypothesis, this is what we focus on for the interpretation. We're putting that p greater than 0.25 in context based on our decision that we decided to reject the null hypothesis. So because we rejected, we were successful, we say there is sufficient evidence at the alpha equals 0.01 level to conclude that p is greater than 0.25, that the proportion of fleas killed by the shampoo is greater than 0.25. So again, we're going through these same 6 steps: hypothesis, picture, test statistic, p-value, decision, interpretation, to decide what we can conclude based on this sample.